I'd like to thank everyone who's joining us today. Welcome to CNCF webinar, Learning from the Visible Past to Accelerate the Observable Future. I'm Julius Rosenthal. I'll be moderating today's webinar, and we'd like to welcome our presenter today, Curtis Rischuk, Technical Product Manager at Instana. So a few housekeeping items. During the webinar, you're not able to talk as an attendee. There is a Q&A box at the bottom of your screen. Please feel free to drop your questions in there, and we'll get to them as many as we can at the end. This is an official webinar of the CNCF, and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct. Basically, please be respectful of all of your fellow participants and presenters. We'll have the recording and slides posted later today at the CNCF webinar page, cncf.io/webinars. And with that, I'll go ahead and hand this over to Curtis for today's presentation.
Hello, everybody. Glad to be here. Thank you for this opportunity to reach out to you. Thank you for taking the time to join the webinar. I recently did a search using Google on the word observability, and I found there were tens of billions of hits. And what I concluded from that is that observability is either going mainstream or it already is mainstream. And why shouldn't it be mainstream? We have metrics, we have sophisticated and stable tools, Prometheus, the OpenTelemetry beta, logging, there's lots of support. Distributed tracing has a solid history with Jaeger, Zipkin, and Open Tracing. I personally am celebrating the W3C recommendation for a distributed trace context so that we can interoperate. If I step back, I think this is what success looks like when a new concept like observability is embraced. And this is something the observability community should be proud of. But what's next? That's the question posed by this presentation. Please consider this to not answer that question, but it is a kickoff to discuss the future of observability. We're going to touch on some trends. We'll review some practical but often neglected requests from observability users that we ourselves have had. We'll take a look at the past as well. Now, I'm sure you're wondering why that subtitle. What can chocolate teach us about observability? Well, you'll just have to stay tuned for a couple slides. So our first step is to actually define observability. And those tens of millions of hits, I'm sure there are many, many definitions for observability. In this presentation, the chosen definition is focused on an outcome, because observability is really a means to an end. And I paraphrased a coworker's definition, and that definition is, if you're observable, then data is available so I can analyze and understand you. So for us, the outcome of observability is understanding, which is achieved by analyzing data. And where do you need this understanding, this observability the most? Well, in production. And so you need to be able to do this in production. Since trends in motion tend to stay in motion, and we're talking about the future, we need to consider the current trends. I've listed just a handful of trends here that make understanding challenging, and therefore they're a challenge to observability itself. We've already talked about or mentioned that production is becoming the validation environment. Speed is a competitive advantage, and so we see speed increasing everywhere. We see complexity being embraced, and in that embrace, it is tamed. We see complex software managing even more complex software. We have just-in-time structure with functions as a service, where something is ephemeral, it pops into existence, it satisfies some requests, and then it can go away. And infrastructure is becoming less and less visible. I see infrastructure, we talk about hardware, but not even hardware, but runtimes themselves are receding away from us. Now, I mentioned chocolate cake, and you wonder, what does chocolate cake have to do with observability? But wouldn't it be great if observability was like chocolate cake? It was available everywhere. It was customized to your personal taste, and it was really satisfying. But you need a reason to bake a chocolate cake. And you wonder about techniques, and what can you learn from your past experiences? And it's similar with observability. What problems and challenges should observability tackle? There's a saying, when the only tool you have is a hammer, every problem looks like a nail. And so we need to be specific and intentional about what problems and challenges fit under the observability umbrella. What are the best practices? What have we learned as a community that we can distill and we can codify and then build on? What can the past teach us about how to proceed? The past is important. We shouldn't neglect it. So like a layered chocolate cake, I submit that there are 3 layers to this problem space with 3 different personas that have different and interrelated use cases. There would be the business owners who are responsible for business outcomes, developers, and the infrastructure operators, the SREs or the operators themselves. Now, I'm sure that there are several variations we could consider, but let's stick with these 3 for the purposes of the discussion. If we start at the bottom, we have the people responsible for the infrastructure. And when I say infrastructure, I include hardware and runtimes. And an example problem statement is they wonder if they retire this hardware, what services are impacted. At the top layer, we have the business owners who focus on user journeys and business outcomes. How many people press that submit button? And when they change something, they're interested in what services are involved, what services need to evolve to add some new feature or aspect to the user journeys. And then in the middle layer, we have the developers who build the business logic and the endpoints and the communication systems or calls that we call services. And they're interested in answering questions like, what business goals are impacted by these services if I modify the service? Alternatively, looking down, what hardware infrastructure is impacting this service? All of these layers have dependencies. But what kind of data is needed? What are the available data sources? Going back to our definition, it depends on what needs to be understood. Like a well-stocked kitchen, there are staples that you always have on hand. These are your basic ingredients, which for us are metrics, logs, and distributed tracing. But if you need to go deeper in one area, or if you need to go broader, not just deeper, but broad, to understand what's going on, you need additional provisions. You need more than just the staples. And there are other tools that we can bring to bear that can provide deeper understanding. There's code profiling, alerts, there's build system integration, user monitoring, beacons, custom dashboards, trend analysis, time shifting, some AI assistance or custom metrics or more. So we want to bring a well-stocked kitchen to enable understanding. Now, what came first, the ingredients or the concept of the chocolate cake? I'm sure that a well-stocked kitchen was where the first chocolate cake was baked. But what caused the chef to bake that first chocolate cake? Did he go to his pantry, look at the ingredients, and decide, I'm going to bake a chocolate cake? Or did he have a craving for chocolate and he decided to bake a chocolate cake? We don't know. But I am sure that the first chocolate cake was a great success because more chocolate cakes have been baked since then. But you can see on the slide that we have a pretty simple chocolate cake. After a while, plain chocolate cake just wouldn't be very satisfying, so I'm sure the chef decided to bake the chocolate cake that would satisfy many cravings. And he imagined what that chocolate cake would be, using his past experience of what worked, what didn't work, what new ingredients he could bring to bear, and using his new baking skills, he would come up with the ultimate chocolate cake. So we can apply this to the success of observability. What came first for observability? The ingredients or the need? It's not clear. But we do know the three observability pillars were the ingredients to bake the first observability platform. And like the first chocolate cake, observability is a success. But is it now time to think beyond these ingredients? Can we take what the community has learned, maybe start at a different point, and aim towards what observability needs to be in the future? And this isn't a new situation. In our industry, we've had similar circumstances many times. And in the past, people have come together and formed a community and developed a reference model, which became the North Star for that community. And that's what we're proposing here, to develop an observability reference model. Now, why a reference model? Well, a reference model can achieve several important goals. First, it promotes understanding of the broad problem space and solutions. And it does this by defining terminology, the relevant entities, the important relationships, and this establishes a common vocabulary which helps interoperability. It is technology and implementation agnostic, so it doesn't necessarily age out. Finally, it's created by a knowledgeable community so that it has broad applicability. So I propose that we build an observability reference model. We start from a different point. Now, some may not have had experience with reference models, so let's make this a little more concrete by looking in the past. I'll quickly talk about three, I'll call classic reference models. The first model I'd talk about or point to would be the introduction of QA models to understand the infrastructure and scheduling. These are mathematical models that provided insight into utilization and scheduling of resources. And the classic reference here would be Richard Kleinrock's 2-volume set. On another dimension, we have end-to-end business processes with synchronization being described in the Calculus of Communicating Systems by Robin Milner. Lastly is Communicating Sequential Processes by R.A. Horn. And this classic was about understanding system properties that emerged from message passing processes. You may or you may not be familiar with them. What they were helpful formalisms that were technology agnostic, and they focus on key aspects of the problem domain. Their value was that they were tools to understand and reason about the different problem spaces. And I did a quick scan, and these models are still being taught today. They're still relevant because they each describe a dimension of a computing environment. So if we were to develop or to work towards developing an observability reference model, why not begin there? Why not begin with these three reference models just mentioned? If we look to the three personas in the problem space lab, you see that each of those reference models that were just mentioned, they relate to one of those particular personas. So I suggest that there are three dimensions to the problem of observability. There are three dimensions to this problem of understanding. And we can check this by answering those problem statements that those personas had. If we look at the business dimension, the question was, what services are involved in this user journey? And we go from top down. we project downwards, where we have two web pages that make calls into services, and those services themselves make requests to other services, and we would discover which services are involved. At the service layer, we'd ask what hardware or infrastructure is impacting the service, and we could project down as well. Again, trying to show that there are three dimensions to this. Alternatively, we can start at the bottom and work our way up. The infrastructure question is, if I retire this hardware, this host, this server, what services are impacted? We project up to the service dimension. We discover those services. Then the next question may be, what business goals are impacted by these services? And we project upwards as well. Now, not all of the questions can be answered in these three dimensions. There's another class of problems that are cross-cutting. Problems such as, top to bottom, what user journeys have priority? How to map the logical services to actual services? What number of service replicas are needed to support the load? Or where to place the replicas? These questions are answered by really combining bits of information from each dimension. And if you notice in the title, we went from 3D plus 1. So there's three dimensions to the problem, plus 1, and that 1 plus 1 is a platform, which acts as a global scheduler or orchestration agent. So we've arrived here by answering some problem statements and found there are three dimensions to observability, plus 1, which would be the platform. And this is being an informal exploration. But if we've arrived here informally, can we make this more formal? Can we describe these things in a more formal manner so that it's easier to reason about them? If we remove the planes from the previous picture, we're left with a graph of objects and dependencies. So why not start with the descriptive, formal graph model? What are the characteristics that model should have? Well, it should be extensible. It should be able to support semantics or meaning. That is also extensible. And if we look at this graph structure, we had three dimensions. We have three different classes of objects, which would be the nodes. We represent relationships which have meaning between the nodes. And we represent relationships between the dimensions as edges. So nodes are objects and they're typed with attributes. Edges are relationships and they're typed with semantics. We want the ability to reason about this graph, such as deducing or inferring system properties. If we were to go back to those three reference models we talked about, that's the ability they provided, is you could deduce or infer system properties. They had a formal structure that enabled this. And the model should be technology neutral. There is one possibility that I just want to put out there. Again, this is about the future. This is to start a discussion. There may be a better formalism to use, but one that does match this is something called an algorithmic attributed graph grammar. It has almost a one-to-one correspondence about the things we'd want in a formal model, where nodes are objects. Those objects have types and they have attributes. The edges are relationships that themselves are typed, and when they connect with a source and target node, that relationship has meaning. You can form subgraphs for more complex semantics from the nodes and the edges. So your subgraphs can have a much larger contextual meaning. And lastly, using this approach, you can reason or simplify in this formalism by using what are called graph rewrite rules. And you can think of a graph rewrite rule as a template that is compared against the graph, and when it finds a matching subgraph, you can then rewrite the nodes and edges, or you can conclude something from that. And this formalism is technology agnostic. You can implement it through various ways, a graph database, SQL, NoSQL, etc. Again, it's technology agnostic, so it should be future-proof. This is one formalism. Again, there may be others. But what would you use this formalism for? How could it be used? At the beginning, we mentioned that our definition of observability it required to be able to be applicable in production. In my experience, and I validated this with many people, is that there's what I call a root cause triage recipe when you have a problem in production. That recipe, it operates in each dimension, and it can also jump across dimensions. And I myself have followed this when I've been diagnosing issues. I've talked to people with decades of experience, and they themselves find this is just a general recipe, and that we start with an unhealthy object, and we can contrast it from when it was healthy, when were things good. If that doesn't answer our questions, if we aren't able to identify root cause, well, then we move on to typically a healthy object of the same type and compare it with the unhealthy object. Next step would be to examine the dependencies upstream or downstream of the object to see what happened. You may need to check recent config changes in the unhealthy object or the upstream or downstream objects. Alternatively, you could consider whether this unhealthy object was in this unhealthy state prior, and what did you do to fix it? It may be that there's a second order interference happening here. We sometimes call it the noisy neighbor problem. It could be the soft or hard limit was reached. Then there may be a bug somewhere. Now, in trying to diagnose these issues, you move from object to object, and sometimes you run into a dead end. And so it may need to go back several objects, and guess what? You need to start at step one again. Then if you can't actually identify the issues, you might need to move to a different dimension, move up or down on there, and then restart at step one again. So a formal model we would want to be able to represent this triage recipe, be able to reason about it, be able to check, to infer things, and to see if any of these steps was the root cause. And we want to be able to use this in production. So let's look at what a microservice production environment looks like. Here is a picture of an actual customer's environment showing the services and the communication between them. It's a pretty dense cake. And for some reason, it reminds me of that Christmas fruit cake you get that's really so dense. It just seems like that's what it is. And how do you deal with this? Well, you slice the cake. Here's a slice, but it's a pretty big slice. In fact, it may be a slice that represents the user journeys for a single business unit. To get something a little more manageable, you may take a smaller slice, or take that bigger slice and slice it again. And this size of slice can feed an entire team. But if you want to slice for yourself, you may want a custom slice. You want a portion that's suitable for a single person. And our experience has been that different users, based on their role and use case, want to see things differently. They want to size the scope to the problem to be able to understand it faster. So what we learned from this is that being able to slice or scope an environment easily is important because it makes understanding easier. In practice, we've found there are 14 different use cases related to scope definition. 5 of them are shown here. We find that teams would like to group several services or endpoints together for their team. We find that Kubernetes namespace is a grouping mechanism. Location is important, and we find that infrastructure or services are grouped by location. This can be environment, prod, could be staging. It could be by geo. It could be by cloud, or surprisingly by host. It seems what we infer from that is that the hosts act as servers for particular technologies or for particular applications. They can be by protocol. It can also be by technology. But being able to slice the scope to suit the use case and the user is an important practical problem. Sometimes you want to slice the system in a horizontal way and near real time. In this example, I'm interested in understanding all of the dependencies a particular service has. And because the services and dependencies are changing frequently, this is very dynamic, so I almost want a live way to do this. And this is a case where distributed tracing works well. But the discussion so far we've had is about observing an environment. Let's switch it around to talk about the system doing the observing. And just to highlight where we've come, we've talked about a definition for observability. We've laid out some trends and some personas. We've suggested the need for a reference model and some of the more practical problems the reference model should address. And now we're going to take a shift and we're going to talk about the observing system itself. And I'm able to bake a cake, but it requires a bakery to bake 1,000 cakes. And so scaling is important, and scaling up a recipe involves some trade-offs. And scaling up observability may also require trade-offs as well. Sampling is used as a scaling tool in observability, and there are a lot of sampling strategies to pick from. But it isn't clear what the trade-offs are. This is an area where understanding about observability itself is needed. Some might call this meta-observability or meta-understanding. But this is an area where a reference model should help. For example, a side effect of sampling is that it can impact the numerator denominator of the error rate calculation. And what are the trade-offs that one would want to make? Picking a sampling strategy to minimize sampling bias or to bound the error or to understand what to achieve based on my needs. Now, I'm not pointing this out to say don't scale. I'm just highlighting that there's a need to understand how observability can alter the understanding of the system being observed. And a reference model could capture this. So it looks like I'm going to wrap this up a little early. Cakes are baked in a cake mold. So obviously, the mold is important. But the machine that makes the cake mold is even more important, because if it goes wrong, then there will be a lot more bad cakes. In a similar way, how should the observability community mold the next observability platform? what should Observability 2.0 be? That's the discussion that we're hoping to kick off. And what we proposed here as a question, not as an answer, but as a question, we posed the question, does the observability community need a reference model to define the problem space, the terminology, the objects, and the relationships? Would a formalism be helpful to provide semantics that enable interoperability and reasoning? And what challenges should we incorporate beyond the API? And I've highlighted a couple. One is the ability to easily scope. We've talked about triaging and the workflow in production. This is not intended to replace any of the current work, but it's intended to complement and inform the future work. So with that, I'd like to open it up that if you're interested in this conversation, please feel free to contact me. My email address is curtis.hryschuk, there's an H there, @instana.com. And I'm going to open it up for a Q&A. Again, please email me if you're interested in taking the next steps, curtis.hryschuk@instana.com. I do want to also point out as a bonus for joining, we have a crossword puzzle related to observability. Please feel free to go and try it out. So with that, we can turn to the Q&A.
Thanks, Curtis. Yeah, everybody, if you have any questions, please go ahead and ask in the Q&A button down at the bottom of your Zoom screen. We've got a shy audience, Curtis.
Well, I hope that, again, please feel free to reach out. What does Observability 2.0 look like? Throwing that question out to the community and hoping we can start the dialogue.
Yes, and you told them your email. Is there a way to connect with you on Slack, or what's the best way?
I don't have my Slack handle handy at the moment. Email would be best, and then we could start up a Slack channel through as the next step.
Perfect. All right, well, if anybody has any questions, feel free, but I'm gonna go ahead and get started on the conclusion. So thanks, Curtis, for the great presentation, and thank you, everybody, for joining us today. The webinar, again, the recording and the slides will be online later today, and we look forward to seeing you all at a future CNCF webinar. Everybody, have a great day. Thanks.